Welcome, learners, to another deep dive. Today, we're tackling a really persistent challenge with large language models, those unexpected blind spots, and just how difficult it is to make them consistently reliable, especially when you don't have a ton of specific training data. How do you teach an AI to learn from mistakes, not just memorize fixes?
Exactly. It's something we see all the time, right? An LLM is great at one thing, then falls flat on something really similar. And the usual approach, retraining, well, it isn't always feasible, especially when even the biggest models struggle, which kind of stops you from generating good synthetic data too. So yeah, this deep dive, we're going to unpack a pretty fascinating new method that tries to get around these problems.
Okay, great. So our mission today is to explore this novel framework they call reflect, retry, reward.
hmm
The idea is that it helps LLMs self-improve, but not by learning specific answers. Instead, it's about learning how to reflect on their own errors. We'll look at how this can apparently lead to some pretty substantial performance boosts, even for smaller models, using reinforcement learning with just binary feedback, simple success or failure. So let's get into this core idea. Reflect, retry, reward. What's the actual mechanism here? How does a model improve after it fails the first time?
Right, so it works in two stages after that initial task failure. First attempt fails. Then the model generates a kind of self-reflection. It basically analyzes its own prior attempt, tries to figure out what went wrong. Second, it gets another try at the task. But this time, its own reflection is fed back into the context. And here's the key part for the learning. If the second attempt succeeds, the tokens generated during that self-reflection phase, those are what get rewarded using reinforcement learning.
Ah, okay, that's really interesting. You're rewarding the reflection itself, not the correct final answer. Why is that distinction so important? What does that actually mean for how these models learn?
That's really the paradigm shift here. We're optimizing the model's ability to generate effective self-reflections. The goal is effective reflection for general problem solving, not just for getting one specific task right. And this makes the whole approach task agnostic really versatile, because all you need is that simple binary signal, did it work or not? No complex ground truth labels needed for the reflection itself.
Makes sense. And the paper mentions using group relative policy optimization, GRPO, for the RL part. What's special about GRPO here? Why is it a good fit for training this self-reflection skill, maybe compared to something more common like PPO?
Yeah, GRPO is interesting. It's outcome-based. It doesn't need a separate value network like PPO often does. Instead, it estimates the advantages by comparing outcomes from groups of sampled completions. Did this group do better than that group? This makes it really well suited for these sparse supervision settings where you only get feedback right at the end of a sequence.
Okay.
Like, verifying a math solution, it either works or it doesn't. Or checking if a function call executed correctly. It seems to effectively encourage models to kind of push through failure and promote that self-correction loop.
Okay, so to show this actually works, the research looked at experiments on two different tasks: function calling with APIGen and math equation writing with Countdown. Could you detail those tasks a bit and how they actually verified success?
Sure. For the APIGen function calling, a model was marked correct only if it picked the right tool and generated the exactly correct parameters and values, verified by an exact match to the ground truth JSON. Pretty strict. For the countdown math equations, it was correct if it used all the given numbers exactly once, and the final equation evaluated to the target number. The key here was that verification didn't need ground truth labels for the final output equation itself, just the target number or the JSON structure. It could be checked automatically.
Got it. And I thought the way they created a data set of failures was quite smart from an efficiency perspective. Can you explain that approach? I think our listeners interested in training methods would find that useful.
Yeah, that was definitely a tactical move to optimize training. So instead of training on the full data sets from the start, they first prompted each model up to 64 times for every query. And they only kept the queries where the model actually failed, according to their verifier. This saves a huge amount of time, obviously, by not training on stuff the model can already do. But maybe more importantly, it helps build robustness by forcing the model to learn from lots of different ways it can fail. Plus, it allows for really precise analysis of convergence based on the number of unique failed samples it learns from. It's kind of like learning from a real-world stream of attempts.
And drilling down into the technicals a bit, they used the TRL framework and multi-step GRPO. What were some of the key training parameters computational needs, especially thinking about model size here?
Right. They extended the standard GRPO trainer to handle that secondary completion step, the retry. And they were careful to only reward the tokens generated during the self-reflection phase. Models trained for up to 1,750 steps, although they often converged faster. The effective batch size was 256 failures. They used pretty standard GRPO parameters, KL divergence coefficient of 0.001, learning rate of 5e7, typical stuff, computationally. It needed between 4 and 8 H100 GPUs, and they limited experiments to models between, I think, 1.5 billion and 8 billion parameters. They noted there are known scalability concerns with GRPO for much larger models currently.
Okay, let's talk results. They seem pretty compelling. On APIGen, the function calling task, model has got about a 4.5% average boost just from the second attempt with self-reflection, and then another 4.7% average increase after the GRPO training on top of that. What really stands out for you here?
Well, the most fascinating thing, I think, is that smaller models trained with GRPO could actually outperform much larger vanilla models. For example, they showed the Qwen27B instruct model. That's 7 billion parameters after GRPO training. It actually beat the vanilla Qwen272B instruct model on function calling when both got 2 attempts.
Wow, 10 times smaller.
Yeah, 10 times smaller. It really suggests this is a powerful way to get more efficient, high-performing LLMs by improving reasoning, not just scaling up.
That is pretty remarkable. It shifts the thinking about needing massive scale. And for the countdown math equations, the gains were even bigger. An average 5.3% bump from self-reflection initially, then another 8.6% after GRPO training. That's significant. Why do you think the math tasks saw greater improvements?
Well, the paper speculates, and it seems plausible, that the baseline performance on the math tasks was just lower to begin with.
More room to grow.
Exactly. More headroom for improvement. And maybe the nature of math problems, where you can often pinpoint a specific calculation error, makes a self-reflection process particularly impactful. It's easier to identify what to fix.
That makes sense. There was also a qualitative point made, comparing this to chain of thought prompting. They observed that the trained self-reflections were often shorter and clearer. Why might being more concise be better here? It seems counterintuitive sometimes.
Yeah, it is interesting. With chain of thought, sometimes more verbosity seems correlated with better reasoning, right? But here, the GRPO-tuned model seemed to produce reflections that were more generalized, less redundant, more to the point. It's like the model learns to abstract the core error pattern more effectively, rather than just spitting out a long, rambling justification. That efficiency in the reflection seems key.
And the elephant in the room with any fine-tuning, catastrophic forgetting.
Yeah.
Did the models forget their general knowledge while learning this reflection skill?
That's always a concern, definitely. But the results here were actually quite positive. They found minimal catastrophic forgetting. Performance on broad benchmarks like MLU Pro, GSM-8K, HeliSwag, Math, it all remained pretty stable, often less than a 1% drop compared to the base model, and sometimes even slight improvements. So it really reinforces the idea that this isn't narrow task specialization. It seems to be enhancing a more general reasoning capability.
Diving into the error analysis adds another layer. It sounds like the types of errors changed after training. For instance, smaller models got much better at choosing the right tool and function calling. While for math, they mainly learned to use the correct numbers, even if the final target calculation was still sometimes off. That gives real insight into the learning process, doesn't it?
Absolutely. It shows the training isn't just a blunt hammer. It's actually refining specific parts of the model's error correction abilities. Improving tool choice suggests, a better grasp of the overall goal. Getting the numbers right in math points to better handling of constraints. This kind of detailed analysis helps us really understand how these models are getting more robust, what specific reasoning skills are being sharpened.
So bringing it all together, what's the big picture here? This deep dive seems to highlight a really powerful way to boost LLM performance, teaching them to get better at self-reflection itself, rather than just memorizing correct answers for specific tasks.
Exactly. It's an indirect approach, and importantly, it only relies on that simple binary success-failure signal. That really opens up possibilities for making models more reliable and useful, especially where detailed feedback is scarce or expensive to get.
Right. So the core takeaway for you as someone following this space is probably the disruptive potential here. If rewarding reflection lets smaller models punch way above their weight, potentially outperforming models 10 times their size, and if it improves general reasoning without causing forgetting, what could that mean for the future? Think about LLM architecture, deployment, especially maybe in places where computational resources are tight. Definitely something to ponder as you continue your own deep dives.